All right, so today's topic is circular motion of this free demo class. And apart from this, before starting out with the topic, I wanted to explain the paper layout, okay, of A2 chemistry first. Okay, in A2 physics, oh sorry, not chemistry, physics. Okay, in A2 physics, you have two papers, okay, paper 4 and paper 5. Paper 4 has almost 10 to 15 questions, okay, and it has 100 marks. And paper 5 has approximately two questions, two or sometimes three questions, and this is of 30 marks only. And this paper 4 is the paper on which your grade depends. Okay, this is the major grade determining paper of your A levels. Okay, if it has approximately 44% weightage, okay, and if you've done well in your P4, then you can save your grade or you can improve your grade. Okay, but if your P4 is messed up, God forbid, then your grade is messed up. Okay, so P4 is the major paper, and this resembles your P2 from your AS, but the only difference is that it has more number of questions, more marks, and a bit more difficult questions as compared to your P2 from your AS. Okay, right. So this was the paper layout. Let's start out with today's topic: circular motion. Okay, guys. So circular motion. You guys did a bit of this in your O levels. Actually, just that famous MCQ that used to come in O levels of identifying the direction of the force which is responsible for an object moving in on a circular path. Okay, so now what is circular motion? Okay, circular motion is basically the motion that is exhibited by an object that moves over a circular path. Simple. Okay, so if for example I have this particle over here, this blue colored particle, and if it moves over this green dotted circular path relative to this fixed point, fixed center, then it is moving in circular motion. Okay, this is the basic, the most simplest definition of circular motion. And now, guys, something that you've done in O levels, what is responsible for the circular motion? It's actually a force that acts towards the center of the circle, and it is called the centripetal force. Okay, what is this force called? It's called the centripetal force. Its direction is perpendicular to the direction of velocity of this object. Okay, if this is the direction of velocity of the object, okay, so the force must act perpendicularly. It must act at a 90-degree angle in order to move this object in a circular path, okay, over a circular path, right? So this force is actually the cause of the circular motion. The cause of circular motion. So, right guys, so it's clear what circular motion really is. It is nothing but the motion of an object moving over a circular path. Now, and the cause is the centripetal force. There are two types of circular motions, okay, a uniform and a non-uniform circular motion, uniform circular motion and a non-uniform circular motion. Okay, what is a uniform circular motion? Uniform circular motion is that circular motion in which this velocity's magnitude, or I should rather say the speed of the object, is constant, is uniform. Okay, if the speed is uniform or the speed is constant, guys, remember I'm using the term speed, I'm not using the term velocity, because speed is actually a scalar and it does not depend upon the direction of the object. Okay, and speed, if stays constant, in that case that circular motion is called uniform circular motion. But if speed keeps on changing, then it's called a non-uniform circular motion, or it is also called it is also called variable circular motion. And guys, in our A2 syllabus, we don't have non-uniform circular motion in our course. Okay, we only have to deal with questions from the uniform circular motion. Okay, so you don't need to worry about the non-uniform circular motion. Okay, so everything clear so far? Any question? what circular motion is, what is this centripetal force, its direction, perpendicular to the direction of the velocity. Shoaib, Hassan, Hussain?
No, sir.
No,
Okay,
sir.
right. So let's begin. Continue. Okay, so this was an overview of what a uniform circular motion really is. Now, a few terms that we need to identify before we move ahead. Okay, for example, there is an object that moves over this circular path. Okay, and this is actually this particle, and there is a central point over here. Okay, this is a center, and the direction of the centripetal force is directly towards the center of the circle. Direction of velocity of an object is always tangential to the circular path. It is always a tangent, okay? It is a tangent to this circle. This is the direction of velocity of the object. And this velocity is known as linear velocity, okay? And its direction is always tangential to the circular path. I hope you guys know what tangential means. Okay, tangent is any line that cuts the circle at one point only, okay, and makes a 90-degree angle with its radius. Okay, this angle is 90 degrees. Okay, anyways, and this distance from the center to the circumference is known as the radius of the circle. You guys are already familiar with this term. And this is the central point. This is the linear velocity. Okay. Now, if the object moves from this point A to the point B over here, okay, let's say this point B is the final position of the object. It covers a certain angle, right? It covers a certain angle in this anti-clockwise direction represented by theta. This angle is known as the angular displacement of the object, okay? The angle which is swept, the angle swept by an object moving in circular motion, by an object in circular motion is angular displacement, okay? This definition of angular displacement was once asked for 1 mark, okay? And this is the definition. The key term was the angle swept, okay? This was the key term that carried this mark. So what is angular displacement? It is just simply the angle which this object covers while it moves over this black circular path. The angle that it makes or that it covers with the with the center, okay, in between the two radii of the circles. So this was angular displacement. Now, okay, the next term that we need to define is radian. Okay, guys, what is radian? Radian is actually a unit of angle. Okay, it is actually a unit, just like degrees. Remember, we used to measure angle in degrees in math. Okay, in math we measure angle in degrees or in radians. Okay, radian is an angle. Okay, and the conversion factor, we can convert the angle in degrees to angle in radians as well. How? Well, by using this relationship that pi radians is equal to 180 degrees. Okay, this was about the radian. Okay, well, how to define a radian? Okay, a definition of radian is almost always asked for 1 to 2 marks. Okay, how to define a radian? It is a unit of angle, but this is not the definition of a radian. Okay, to define the radian, we'll need to look at a few terms first. This radius and the arc length. This arc over here that the object has covered, this arc length can be represented by S. Okay, and this is also the radius. This length, this blue line, is also the radius of the circle. Now, from math, there is a formula to calculate this arc length. Okay, how to calculate the arc length? When the angle given is in radians. So arc length is equal to the product of radius and angular displacement, or the angle. S is equal to r theta. This is something you've done in math. Okay, this is a formula you'll need to remember. Okay, the formula for calculating the arc length. Okay, so for example, if I have an object moving on a circular path, and its radius is, let's say, 2 meters, and the angle that it covers is, let's say it's 0.5 radians. Okay, for example, it covered an angle of 0.5 radians. So how to calculate this arc length that it covered? Okay, this arc length S. How to calculate that? By using this formula. Okay, S is equal to r theta. Okay, where r is 2, r is the radius, multiplied by theta is 0.5 radians, and it will give you 1 meter. Okay, 1 meter is the angle that it covered if this radius is given in meters. Okay, if this radius was in centimeters, then this would have changed to centimeters. Okay, so this is the formula for calculating the arc length. Okay, so clear? Now, using this formula, we can define what a radian really means. Radian is a unit of angle, right? So S is equal to r theta. To define this angle, to define this theta, to define the radian, rearrange it. Radian is equals to S upon r. Okay, so now S upon r. So it is the ratio of the arc length to the radius. Or you could just say that it is the angle which is swept by an object moving by an object when it covers an arc length equal to the radius. Okay, if arc length and radius are equal, then obviously you'll get radian. You'll get 1 radian. If both of them are equal, let's say both of them are 2 meters. Okay, so what will you get? You'll get 1 radian, right? The definition of this 1 radian is the angle which is swept by an object moving in a circular path when it covers a distance or an arc length or just the distance equal to the radius of that circle. Okay, this is the definition of a radian, and this is almost always asked for 1 to 2 marks. Guys, this is what you need to remember. Okay, in several places in the marking scheme, the wording keeps on changing a bit. Okay, so you could just go with the latest marking scheme, according to which the definition is slightly different. Okay, it's actually the same, but the wording is a bit different. Okay, which is actually the marking scheme says that the angle swept by an object in circular motion when it covers a distance equal to the radius. That's a definition given in the past papers and the marking scheme. Okay, or just one more definition so that you guys don't get confused when you look at different marking schemes. The angle subtended from the center of a circle when arc length is equal to the radius. So all the three definitions actually mean the same thing, and I would go with this definition. This is the best definition. Okay, so just learn this definition. Okay, the angle which is subtended by an arc which is equal by an arc which is equal in length to the radius of a circle. Okay, for example, if this is the arc, if this arc length is also r, and if this radius is also r, then this angle over here is 1 radian. Okay, this is the definition of a radian. This is almost always asked, guys, so you better remember this definition. All right, now after we've defined what radian means, okay, then an angular displacement has been defined as well. Now the next term that we need to define is angular velocity. And angular velocity is represented by the symbol omega. Okay, what is angular velocity? Guys, before going on to angular velocity, you guys know what velocity is, right? From your AS, velocity is the rate of change of displacement, right? And this is a vector quantity. So if the direction, it is vector quantity, so it is direction dependent, depends upon the direction. So if the direction of an object changes, then the velocity changes. So if I ask you that in a uniform circular motion, is the velocity changing or not? So what are you supposed to answer me? Anyone? Okay, anyone guys. Does the velocity change in a uniform circular motion or not? Uniform circular motion, remember that the speed is constant, but is velocity constant? No. Okay, correct, Hassan. You are very correct. Velocity is not constant. Velocity keeps on changing. The reason is because it is a vector. Yes, it is a vector. Now I'll explain why. Because at every point, the direction of this velocity, the direction of the speed keeps on changing. Okay, although the speed is constant, the object is moving with a constant speed, but its direction at every point is changing. So since its direction is changing, therefore the velocity keeps on changing. Okay, so if the velocity keeps on changing, then we can say that even in a uniform circular motion, the object accelerates. Okay, the object accelerates. What is acceleration? It is the rate of change of velocity. So although the magnitude of velocity is constant, which is the magnitude of velocity is speed, but the direction of velocity keeps on changing at every point. Therefore this object, it accelerates. Okay, velocity keeps on changing. So the rate of change of displacement is velocity, okay, which is dependent upon the direction. Now, what is angular velocity? This was just the rate of change of displacement, right? If I add the term angular in here, angular displacement, it becomes angular velocity. Okay, so I could just simply say that this is the rate of change of angular displacement. Okay, and we can also write it mathematically. Angular velocity is equal to the change in the angular displacement. Angular displacement is this angle divided by time. Okay, divided by time. Why did I divide it by time? Because this is rate. Okay, rate means with respect to time. So the change in the angular displacement with respect to time is the angular velocity. And velocity can also be written in a similar way. Velocity is equal to the change in distance, the change in displacement divided by time. Okay, but the difference is this is linear velocity, meaning along a straight line, and this is angular velocity. Okay, Now we've got the definition of angular velocity as well. So far, the formulas that we've covered are V is equal to R omega. Oh, sorry, not this one. This one is about to come. We've covered S is equal to R theta, and we've covered the formula of angular velocity. All right. Now, for an object moving in the circular motion, what is the maximum? Okay, let me ask you something. An object starting out from this point A completes one cycle and returns back to this point A. The time that it takes to complete one revolution, what is that time called? Any idea, guys? The time in which it completes one revolution. This object completes one revolution. What is it called? Any idea? The time period, correct. The time period. So if I were to ask you to define what time period is, this is something you've done in the waves chapter from AS as well. It is the time taken to complete one revolution. So, and guys, the angle, what is the angle that this object covered while it moved one complete circle? What was the angular displacement that it covered? Can I say it covered 360 degrees while it completed one cycle? Correct? Now, convert this degrees to radians, because in physics over here in this chapter, we are going to deal with angles in radians. So in radians, the angle is equal to 2 pi. Okay, 2 pi in radians. Now we've got our angle, we've got our time period. So the formula for omega can be modified for one complete revolution to 2 pi divided by capital T. Okay, but guys, remember, this T is not just any time. This is specifically the time period of an object to return back to this point A from where it started. Okay, now this is another formula for omega. And guys, remember from AS, what does 1 upon T represent? What is 1 upon T equal to? Any physical quantity you guys remember that 1 upon T is equal to? 1 upon T is equal to frequency. Yes, correct. It's equal to frequency. Just a moment, guys. Okay. Yes, correct. It is equal to frequency. So 1 upon time period is equal to frequency. So I can replace this 2 pi upon T by 2 pi into 1 upon T. And I can write this formula as 2 pi into F, because this 1 upon T is actually equal to the frequency. So now this is the formula of omega that we've derived. Omega is equal to 2 pi F. And this is actually the most frequently tested formula for omega. Okay, a very frequently tested formula. So I would suggest just remember and learn this formula. Okay, guys, this omega, I told you that this is the angular velocity, right? This omega is also called angular frequency. Okay, sometimes in the past papers they ask you to calculate angular frequency. What did you not get, Hassan? This 2 pi into 1 upon T stuff? I've just replaced this 1 upon T by the frequency, 2 pi F. You know that 1 upon T is equal to the frequency, right? So just replace this 1 upon T by the F. Okay, so it will become 2 pi F. Omega equals 2 pi F. Okay? Right. Now, this omega, the angular velocity, is also known as angular frequency. Okay, so sometimes in the past papers they use this term as well. They ask you to calculate the angular frequency, and they actually are asking you to calculate the omega. Okay, So this is the formula that you use. And the units, what are the units for omega? Well, the units for omega that are usually used, actually, the units for omega, what do you guys think the units for omega are? You can derive them from this equation over here. Omega is equal to, what are the units of angle? Units of angle, the unit of
Radian.
angle is radian, and the unit of time is second. So it becomes radian per second. Okay, this is the unit, the SI unit of omega. And what is the unit for frequency that is used over here? The unit for frequency in this case is revolutions per second, okay, or revolutions per minute. Okay, both of them are used in the past papers. This is actually these units are derived from the definition of the frequency, that frequency is actually the number of revolutions which are produced in 1 second, okay, or 1 minute, or per unit time. Okay, so so wherever in the question it's the number is given with these units, you guys need to understand that they are talking about the frequency. Okay, so for example, if the examiner gives you this unit, this number over here, the object moves with or the object completes 25 revolutions in, let's say, 5 seconds, calculate the frequency. So you can easily calculate that by just dividing, by using the formula for frequency, by dividing this 25 revolutions by 5 seconds. Okay, you'll get 5 revolutions per second as the frequency. Okay, now this was the frequency, this was omega. So now the new formula for omega that we've done is this one, omega equals 2 pi f. Now I'll list down the formulas that we've done so far. We did the formula for the arc length, S is equals to r theta. We did the formula for omega, which is equal to theta upon t. We did the formula for velocity, which is equal to displacement upon time. Now, and we also derived another formula for omega, which is equal to 2 pi f. Now, using this formula over here, we are gonna develop a relationship between the linear velocity and the angular velocity. Okay, and let's see how is that gonna happen. Now, guys, you know that S is equal to r theta, right, from the formula above. If I divide both the sides, by time, just a moment, guys. Okay, if I divide both the sides by time, okay, by the t, this side becomes s upon t. This s is actually representing your displacement, the linear displacement, and t is representing the time period. What is displacement upon time period? Is that equal to the velocity? Is that equal to the linear velocity? Yes, it is. And what is this theta upon t? Theta upon t is actually the rate of change of angular displacement, right? So p is equal to r multiplied by omega. Theta upon t is omega and s upon t is v. So this is the next formula that we've derived, and this is also a very important formula, okay, that relates linear velocity and angular velocity. Okay, I'll repeat. Basically, what we did was, actually, I'll take another approach to this question now, to this derivation actually. You know that v is equal to s upon t, right? You know that velocity is the displacement upon time. Now this displacement, I told you this s can also be written as r theta. S is equal to r theta. This linear displacement is equal to r multiplied by theta. So just plug in that r theta over here in place of s, and you'll get the formula will become r theta divided by capital T, right? And now in this formula, this theta upon T, what does that represent? This theta upon T actually represent your angular velocity, omega. So the formula modifies to R multiplied by theta upon T will be replaced by omega. Okay, so this V is equal to R omega. Okay, where V represents the linear velocity of an object moving in the circular motion. R represents the radius of the circle. And omega represents the angular velocity. Okay, now do you get it, Hassan? Now, we've got our linear velocity, we've got an equation for angular velocity, we've got the frequency. Okay, so these are the few formulas we've done so far. I'll tell you the situations in which you'll use them in a bit. Actually, when an object is moving in circular path, okay, and the examiner gives you the linear velocity, and let's say the linear velocity is 10 meters per second, and he also provides you with the radius of the circular path, let's say 2 meters, and he asks you to calculate the angular velocity. So how are you going to calculate the angular velocity? By using the formula V is equal to R omega, right? You could plug in this 10 in place of V, you can plug in the 2 in place of R, and omega as it is, omega becomes 5 radians per second. Okay, the difference between angular and linear displacement is that linear displacement is actually this circular displacement that is covered. Okay, linear displacement is actually the displacement covered from a certain point. Okay, it is the normal displacement that you've been doing since your AS. The displacement that you did in AS, that was linear displacement. The distance which is covered, the shortest possible distance between 2 points, is linear displacement. But angular displacement over here is the angle which is covered. Okay, we defined the angular displacement in the very start, the very beginning, right over here, somewhere here. Yeah, right here. The angle which is struck by an object moving in circular path is the angular displacement. Okay, this angle over here, this is the angular displacement, and that displacement over there, or the distance which is covered by this object, by this length of the arc, is the linear distance or displacement. Okay, which is covered by the linear speed or linear velocity. Clear, Hassan? The linear and angular displacement. Just
Yes, sir.
consider the linear displacement as the displacement which is covered by the linear velocity. Okay, and the angular displacement by the angular velocity. Or you could just say that angular displacement is the angle, which is just the angle which is made or which is covered at the center of the circle. Okay, now let me test you guys now a bit. For example, I have an object over here at this point A, and it moves in a circular path and reaches this point B. Okay, it covers a certain distance. I have another object at the point C, and it moves from point C to the point D at the same time. Okay, at the same time, in the same time interval. Now, what are the, let's say I call this as V1, the object over here as v2. Now guys, how will their angular displacement and how will their linear displacements vary or linear distances vary? Oops, I'm sorry. Okay, theta 1 and theta 2, and I'll call this as S1 and S2. And okay, wait, let me make it even better. How will the linear velocities and the angular velocities vary? Now guys, will they be equal, greater, or less than? Which of the two objects will have greater linear velocity? First tell me about the linear velocity. Sorry, okay, just tell me about the angular velocity first, because that's a bit easier to identify. And this is the angle that
It will be equal.
angular velocity is going to be equal. Okay, correct. Why is it going to be equal? Any reason?
The angular distance is same for both.
Yes, the angular displacement is the same for both of them. Correct. And the time that the time they took to travel this distance was also the same. Okay, and how will the linear speeds compare? How will the linear velocities compare? Any idea?
So V2 will be greater.
V2 will be greater. Okay, Hassan, what do you say? Yes, correct. Actually, V1 will be greater. Reason? Reason is because this arc that it traveled, this is longer than the arc that the V2 traveled in the same time interval, okay? Speed is equal to distance upon time, right? Time is the same, but this S1 is greater for V1 as compared to S2 for V2. Okay, Hussein, get it? Yes, S1 is larger, correct. All right, guys. So so far we've covered velocity, angular velocity, radian, and angular displacement, and their associated formulas. Okay, omega had two formulas. One was theta upon t, and the other is 2 pi f. Okay, now let's move on to the major stuff. If an object moves over a circular path, it moves over a circular path due to the centripetal force. How to calculate this centripetal force now? In O levels, we used to identify the direction of the centripetal force, but we never we never used to calculate the centripetal force in O levels, okay, because we didn't know how to calculate it in O levels. But now over here, we can calculate centripetal force as well. Now I'm going to show you how to do that. First of all, guys, I just told you that circular motion, an object that moves in circular motion actually accelerates, right? It accelerates. And since if the object accelerates, and I also told you that according to Newton's second law of motion, F is equals to ma, the direction of the force, the resultant force, in this case, the resultant force is this centripetal force, and the direction of the acceleration are exactly the same, okay? From AS we know, and from Newton's second law, we know that force and acceleration are in the same direction, and this is always the case, same direction, okay? I'm actually talking about the resultant force, okay? This is the net or the resultant force that is always in the direction of the acceleration that it produces, okay? And acceleration and acceleration and the resultant force are always in the same direction. So now the acceleration which is produced due to this centripetal force is also in the same direction as the centripetal force, and it is also towards the center of the circle, and it is known as the centripetal acceleration. Okay, this is called the centripetal acceleration. And there is a direct formula of calculating the centripetal acceleration. Centripetal acceleration is equals to v squared divided by r. Okay, and you don't need to know the derivation of this formula. Okay, you just need to memorize this formula. Okay, how to calculate the centripetal acceleration? V squared upon r. What is v? V is the linear velocity or the tangential velocity. Okay, the velocity which is a tangent to the circle, a tangent to the circular path. In this case, it is shown by this green arrow over here, and this r represents the radius of the circle. Okay, using this formula, we can calculate the centripetal acceleration. So now we know how to calculate the centripetal acceleration. Can we calculate the centripetal force as well? Yes, Hassan, you have a question? You are still confused. Confused in what? This is just a formula to calculate the centripetal acceleration. There is nothing to be confused about here. About linear and angular velocities. Okay, just consider, okay, let me tell you something. Linear velocity is this velocity over here. Okay, this velocity, the tangential velocity is the linear velocity. Okay, and omega is the angular velocity. The rate of change of linear displacement is linear velocity. The rate of change of angular displacement is angular velocity. And the formula for omega is the theta, the angle in radians divided by time, whereas the formula for v, for the linear velocity, is the linear displacement divided by time. The only difference between them is that this is the linear component, the angular component, and v is the linear component, because the displacement is linear over here and the displacement is angular over here. Okay, the displacement, this is the arc that is being covered, and this is the angle that is being covered. Okay, ab samajh aaya? You get it now? All right, cool. Now moving on. I told you how to calculate the centripetal force, centripetal acceleration, okay, v squared upon r, where v represents the linear velocity, this velocity over here, this green velocity. Now, how to calculate the centripetal force? How to calculate the centripetal force? Okay, guys, from Newton's second law, we know that centripetal force or any resultant force is equal to ma. F is equal to ma. Okay, but in this case, it's gonna be the centripetal acceleration. Fc is equal to mac. Just plug in the expression of AC in place of AC in this formula, and you'll get a formula for centripetal force. Okay, this formula for centripetal force becomes m multiplied by v squared over r. Okay, I've just plugged in v squared upon r in place of AC over here, and the formula for centripetal force, the first formula for centripetal force becomes mv squared upon r. Okay, there have been questions in which the examiner asked us to calculate the magnitude of the centripetal force, and this is the formula. This is the first formula that we can use to calculate the centripetal force. Okay, everything clear so far? Any question? Okay, moving ahead then. This is one way of calculating the centripetal force. Now, another way of calculating the centripetal force. Okay, this is the first formula. We know the centripetal acceleration is equal to v squared upon r, okay? And we also know that this linear velocity and angular velocity are related to each other by this formula, v is equal to r omega, right? If I plug in this formula in place of v, I'll get a centripetal acceleration equation in terms of the angular velocity, in terms of this omega, okay? So now, let's plug them in here. R omega squared, okay, this is squared, so therefore it got squared divided by r, and so it becomes r squared omega squared divided by r again. The r's cancel out, and the formula that you get is r omega squared. So centripetal acceleration is also equal to r omega squared. Okay, this is the second formula that you get. So if this is the formula, then what is the corresponding centripetal force formula? It is equal to mr omega squared. Okay, I just plugged in AC expression in this formula. Okay, F is equal to ma ki jagah I just plug in r omega squared. Okay, And so I got Fc equals to mr omega squared. Okay, so this is the second formula for centripetal force. Okay, these are the two most important formulas for centripetal force and centripetal acceleration. And almost all, okay, all the questions are going to be solved by using this formula. Okay, you can even derive a formula in terms of velocity and omega only for centripetal force, but that formula is not used much. Okay, but I'll still derive it. These two formulas are enough. V is equals to r omega can also be rearranged by making r the subject. R is equals to v upon omega. Now place this into the original AC expression of v squared upon r. Okay, instead of r, place v upon omega. So it becomes v squared upon v, and since omega is in the denominator, it will go up over here. Omegas cancel out. The formula that you get is omega and v. Okay, so centripetal force is equals to omega v. So centripetal acceleration is equals to omega v, and so the corresponding the centripetal force will become m omega v. Okay, so this is the third formula for centripetal force, but this formula is not that frequently used. Okay, this is the third formula in terms of omega and v only, excluding the radius. Okay, so we've got the three formulas for centripetal force. Okay, mv squared upon r, mr omega squared, and m omega v. So when the examiner gives you the angular velocity and the radius and the mass and asks you to calculate the centripetal force, this is the formula that you are going to use. Or if the linear velocity is given and the radius is given, then this is the formula that you are going to use. Okay. So I'll list down the formulas together. Okay. Centripetal force is v squared upon r. Guys, I would suggest don't even learn this formula. You could just remember this by only learning the formula for the centripetal force. Centripetal force is mv squared upon r, right? Exclude the m and you'll get the expression for AC. You'll get the expression for acceleration. The second formula is r omega squared. Corresponding centripetal force formula becomes mr omega squared. Okay, exclude the m, you'll get the expression for AC. Again, the third formula is v omega. Okay, so the formula becomes mv omega. But this formula is not that important. Okay, this is not important. The first two formulae will allow you to solve each and every question in the past papers. Okay, so now this was the centripetal force. The first one is for linear velocity. Yes, correct. This formula is for the linear velocity. Remember this v symbolizes linear velocity, and omega symbolizes angular velocity. And I've defined both these terms earlier in the class. Second, third angular velocity. What do you mean by that? Not yeah, exactly. The second one is also for just angular velocity, and the third one is a combination of both of them. It involves linear velocity and angular velocity as well. Okay, is a formula of mv omega. But I told you earlier that you don't need to know, even if you don't know this formula, you can solve every question by using the first two formulas alone. Okay, yes. Now, so this was centripetal force, centripetal acceleration. So all the formulas have been completed that you are going to use. Okay, I'll just quickly jot them down. V is equals to r omega to calculate the linear velocity. Omega is equals to 2 pi upon 2 pi f. Okay, omega is equal to theta upon t. S is equals to r theta. AC is equals to v squared upon r. Or AC is also equals to r omega squared, or AC is equals to v omega. Okay, and centripetal force is equals to mv squared upon r, and centripetal force is mr omega squared, and centripetal force can also be equals to mv omega, right? So these are all the formulas that we've covered so far, and these are the formulas you're going to use in your circular motion throughout this chapter. Okay, no other formula needed. And yeah, this formula over here, this can also be written as 2 pi upon t. Okay, replacing the frequency by the time period. Okay, trust me guys, in A2 you are gonna deal with lots and lots of formulas, almost around 80 formulas in the entire A2 syllabus, okay? So get used to these formulas. Okay, I would suggest you just go over them, learn them, etc. Now we've got cases, specific cases that usually are most frequently tested in the past papers. Okay, so let's do them quickly. Okay, first case is vertical circle. What happens in case of vertical circles? In case of vertical circle, an object moves vertical in a vertical circle. Okay, this is the ground over here. This is the ground. Okay, and vertically, an object is moving over a circular path. Okay, so just for example, if you imagine a windmill also has its wings going on like this, right? Moving in a vertical circle. So they also form a vertical circle. For an object to be moving in a vertical circle, and for example, this is the central position. Okay, in this vertical circle, the points that we are interested in are the points directly above this central point and the point which is directly below the central point. Okay, below the center. Okay, this is the lowest possible point and this is the highest possible point. Now, if an object is at the lowest possible point, what happens is that its weight acts downwards. Okay, and for example, this is actually a stone. This object is actually a stone attached to a string. Okay, and that string has a certain amount of tension in it, this tension force. Okay, now this tension and the weight are there. Now guys, this object moves in a circular path. Why is it moving in a circular path? The reason behind every circular motion is what I just told you in the start of this lecture, is the centripetal force, right? That centripetal force also acts towards the center of the circle. Okay, now this tension and the weight are the centripetal, they are forces. They are two different forces. Okay, but centripetal force is the resultant force. Remember, centripetal force by definition, it is the constant resultant force that acts perpendicular to the velocity of an object moving in a circular path. Okay, so now what is going to be the resultant of this tension, and what is going to be the tension and weight? Okay, since the object is over here and it's not going downwards, so this tension has to be greater than weight, right? So tension minus the weight is gonna be your centripetal force. Okay, tension is greater in magnitude, therefore I subtracted this weight from the tension. Okay, tension is greater in magnitude, that's why this stone is not going downwards. Okay, it's staying at its own position, and it will eventually move on and on and on and on. And then after it moves to the maximum position over here, at this maximum position, the weight acts downwards, tension in the string also acts downwards, right? And now both of them are acting downwards, so what's going to be their resultant? Both of them are going to act towards the center, so their resultant is going to be tension plus weight, because they are both acting in the same direction, and their sum is going to equal the centripetal force. Okay, so these are the two equations that are very important, okay, in case of a vertical circle, because sometimes the examiner asks you to calculate the centripetal force of an object moving in a circular path, okay, and he just gives you the tension in the string at the lowest point. Okay, now guys, tell me something. Out of the two formulas over here, in which of the two formulas will the magnitude of this tension be greater, in the red formula or the green formula? Any suggestion? the magnitude of tension. Well, to calculate the magnitude of tension, you'll just need to rearrange this formula to make T the subject. So T is equal to Fc plus W, okay, in this first equation over here, and T in this case is equal to Fc minus W. So the value of T in the first equation, the equation for the lowest position, the lowest point, is greater because they are being added up. So guys, remember something, that since the value of the tension is maximum, the value of the tension in the string is maximum at the lowest position, therefore this object, the string, is most likely to break at the lowest position. It is most likely to break at the lowest position, okay? Similarly, if you talk about the highest position, this string is least likely to break at the highest position. Yes, correct, Hassan, red. Okay, this green equation is for the maximum position where the tension is the least, because the centripetal force the weight is being subtracted from the centripetal force. And if you talk about the lowest position over here, the tension is the greatest because they are being added up. Okay, now these two equations are very important. Now apart from this, if I take the red equation for the minimum position, I told you that tension minus weight is equal to the centripetal force, right? So you could rearrange, you could change this formula by plugging in instead of weight, you could just plug in mg, right? Instead of Fc, you could plug in the formula for Fc. Okay, what is the formula for Fc? Any of the three formulas that we just did, mv squared upon r, or mr omega squared, or mv omega. Okay, any of those formulas. Okay, mv squared upon r. Okay, so this is one equation that you could get for the lowest position. Okay, guys, so remember, for an object moving in a vertical circle, the centripetal force, the magnitude of the centripetal force, it keeps on changing and changing. Okay, it keeps on changing. Okay, at the least position, it becomes, okay, what happens to the magnitude of the centripetal force at the least position? The magnitude of the centripetal force at the least position becomes minimum, and the value of the centripetal force at the maximum position becomes maximum. Okay, I'm talking about the centripetal force, I'm not talking about the tension. Okay, remember that. At the maximum position over here, the tension is minimum, but the centripetal force is maximum. Okay, from this formula over here, tension is minimum. Oh, sorry, this formula is for the lowest position. From this green formula over here, centripetal force is maximum, but the tension is minimum. Okay, and at the least position, vice versa, tension is max and centripetal force is minimum.